is a master student.
Not anymore.
PhD student.
Not anymore.
In the French is now becoming an expert on two-photon emissions, and we will talk about two-photon emission dynamics and other interactions.
So, welcome everyone. My name is Gabriele Ippolito, and today I'm going to talk about two-photon emission dynamics with quadratic light matter interaction. Very briefly, this presentation will deal with my thesis project, plus some stuff that I've started doing with my PhD. I'm really new. This is my first month as a PhD student here, and this is my first group meeting with everyone. This is a little summary of the presentation. We will start just reviewing some old school of light matter interaction, like spontaneous emission or vacuum radial oscillations in cavity QD. Then introducing, for those who are less familiar with the concept of coupled cavity arrays, indeed the concept of coupled cavity arrays and why they are interesting nowadays. Next, we will move on to my thesis project. I'll explain you what I did and the ongoings that I'm currently focused during my PhD. So let's start very quickly by saying that all of us know what happens in free space, right? If we put an atom in free space, this is weakly coupled to the field, in particular with a continuum of energies, and this leads to the well-known spontaneous emission. Basically, the atomic population, if the atom is prepared in the excited state, decays exponentially. Here gamma is the decay rate, and on the other hand, the photon escapes. It is not confined. While if we are inside a cavity QD setup, and we describe the light matter interaction via the well-known James Cummings model, we know that the photon is trapped, is confined inside a cavity. So if the atom is initially prepared in the excited state, it emits one photon, then the photon is, after a finite time, reabsorbed by an atom. And we observe this pattern in the excited state population that is known as vacuum radial oscillations. And I would like to say that this type of interaction is referred to as linear interaction, in a sense that matters couples linearly with the field. In other words, matters and field exchange one excitation at a time. Now I very quickly introduce to you the concept of coupled cavity arrays, because this is put between free space and the ordinary cavity QD setups, and they provide a link, a conceptual bridge between the branch of condensed matters and the branch of quantum optics. Indeed, what are coupled cavity arrays? Basically, they are a set of cavities that are tunnel coupled between each other, and they are arranged in a lattice geometry. So we can reproduce the optical analog of the crystalline lattices. For example, if we place the different cavities along a chain, we can recreate a one-dimensional simple lattice, but we can have fun with the geometry. We can reproduce, for example, a square lattice of cavities, or even a graphene lattice with cavities. And this is interesting because this tells us that nowadays we can engineer energy bands depending on the geometry of the coupled cavity arrays, as well as energy band gaps. And the problem we are interested to study is the emission dynamics in coupled cavity arrays. In particular, we have one emitter whose atomic frequency is labeled here as omega 0, and this emitter is placed inside one cavity of the coupled cavity array. And there are two important parameters here. J, there is the opting rate, and G, there is our coupling strength. Depending on whether G is greater than J or vice versa, we can identify two regimes: a strong coupling regime and a weak coupling regime, where J is much smaller than J. To give you intuition why the strong and weak coupling regimes are identified by these conditions, for example, let me say that if an atom is put inside this cavity and it emits a photon, if J is much bigger than G, the photons have the possibility to escape because it prefers to jump along the chain rather than be reabsorbed by the atom. So this is the concept. Very quickly, here I would like to analyze the simple 1D homogeneous coupled cavity array, just for give you an introduction. And for this type, for this type of simple array, one-dimensional chain, this is the single photon dispersion relation of the coupled cavity array. Here you see there is this single photon dispersion relation plotted as a function of the momentum k of the emitted photon. And here we have the corresponding density of states as a function of the energy. Okay, and what I would like to stress here is that you see the density of states manifests divergences at the edges of the band. These are well known in literature as Van Hoff singularities. They are linked to the fact that the density of states indeed diverges in correspondence of the edges of the single photon dispersion relations in lattices in general, not in coupled cavity arrays, so also in crystalline lattices. And also very important, typically these divergences of the density of states are closely related to non-Markovian dynamics that may emerge in the system. And in 1D, there is a very simple but a very beautiful relation between the density of states and the group velocity of the emitted photon. Indeed, the density of states scales like the inverse of the group velocity. Okay, and this, as we see here, and as we will see here very quickly, has an important consequence, because if we consider a weak coupling regime in which the atomic frequency is tuned inside the single photon band, we observe spontaneous emission. Indeed, J is much bigger than G, so photons tend to hop in the adjacent cavities rather than be reabsorbed by the atom. If we are in the strong coupling regime, we observe atomic oscillations. Indeed, now the photons remains localized around the atoms because it doesn't have the time to escape from the atom, because G it's bigger than J. But very interestingly, we observe a new phenomenon that is known as fractional decay, and this happens when the atomic frequency is tuned in the weak coupling regime at the edges of the single photon band. This behavior of the atomic populations suggests that after a finite time, we see that the excited state population stabilize around this value, and the reason why this is called the fractional decay is that it is as if part of the atomic excitation is transferred to the field, while a fraction of the atomic excitation remains at the atom. To understand why this happens, we can recall the link between the density of states and the group velocity of the emitted photons. If you remember, at the edges of the band, the density of states has a divergence. Since the density of states scales like the inverse of the group velocity, in this scenario, the emitted photon is emitted with exactly zero group velocity. Basically, this means that the photon is emitted and stays still in the cavity with the atom. It doesn't propagate, okay? And we can observe directly this behavior by analyzing the so-called photon density, that is nothing but the mean value of excitations in each cavity. For example, if we are in the decoupling regime and we observe spontaneous emission, we observe this, On the here, on the x-axis, we have the cavity index, basically the chain of cavities. On the y-axis, we have time, and we are observing how the photon spreads and propagates along the chain. The reason why we observe two bright lines is that if we set an atomic frequency, we have two resonant modes, okay, and one that corresponds to the photon that propagates rightward, and the other one leftward. If we are in the strong coupling regime, we observe that the photon is emitted, reabsorbed, emitted, and reabsorbed. We observe bright pulses. And if we are in the recoupling regime, we observe a fractional decay. We observe, okay, we observe a bright line here that is localized around the emitter location. The emitter here is located at the center of the chain. And we don't see that the photon stays still in the cavity. Couple cavity rays are also important because they allow us to make simulations of rather complex systems, introducing photon-photon interactions. For example, by introducing Kerr interactions in our Hamiltonian, we can simulate the Hubbard model with couple cavity arrays. And this is interesting because in the Hubbard model, what we call here bound states refers to two photon states in which the two photons are exponentially localized around each other and propagates together along the chain. Here you can see this is the typical wave function for a bound state in the Hubbard model, okay? That is a function of n and m, where n and m are the two positions of the two photons that propagates in the array. And we see that they are exponentially localized in the relative coordinate, meaning that they propagate, but they are forced to be exponentially localized around each other and propagate together. And there was this article from 2020 from Peter Rabel in Munich. That was my supervisor during my thesis project in Germany, that studied how we can observe the formation of two photon bound states in couple cavity arrays from a scenario in which we have two or more emitters, because if we have only one emitter, we do not observe the emission of two photons. But if we have two or more emitters, they describe this second order process that basically consists in one emitter emits one photon, one virtual photons. After a finite time, these virtual photons encounters a second emitter that is in the excited state, and this second emission from the second emitter leads to the formations of two photon bound states, and they become a real couple that propagates in the array. What I did for my thesis project was to analyze the emission dynamics, but with a different type of coupling, because here, as in most of the research in quantum optics, the type of interaction the type of model that describes the light-matter interaction is indeed the James Cummings model. And as I told you, in this model, matter couples linearly with the field. An atom one photon. So in my thesis, what I analyze is the emission dynamics in couple cavity arrays, but now considering a so-called quadratic interaction, in a sense that the emitter does not emit or absorb one photon at a time, but it has the possibility of emit or absorb two photons at a time. And nowadays, this type of interaction described firstly in the two-photon Rabi model, is experimentally feasible. There have been, starting in 2018, several proposals on how to realize such interaction in couple cavity arrays, exploiting, for example, circuit QD. And this is the model I studied. We have an homogeneous one-dimensional couple cavity array that it is described by a simple tight binding Hamiltonian, in which you have an on-site term, the frequency of the cavity, and we have the hopping term, where J is the hopping rate. We can, in principle, consider local Kerr interaction that happens only if the two photons are inside the same cavity. You see, this is a local interaction. And next, we have the emitter term and the quadratic interaction that it is derived from the two-photon Rabi model, but under the rotating wave approximation, because I am only interested in the weak coupling regime here. And to simplify the analysis, we know that the usual James-Cummings model is simple to analyze because the Hamiltonian commutes with the number of operators, and we can restrict ourselves in the subspace with fixed number of excitations. In this scenario, we can still do this restriction, because one can show that Hamiltonian commutes with the, where we put these two in front of the emitter term. Simply, this means that one atomic excitation in our analysis counts as two photons. This is the meaning of these two here. And this is called weighted number operator that leads to the so-called weighted number of excitations. The first part of my thesis project was study this model without accounting for Kerr interaction. We start analyzing the photonic bath, and this is a one-dimensional homogeneous couple cavity array. So the photon dispersion relation is the one that I was telling you a few slides ago, that goes like cosine of the momentum. And in this case, where the photons do not interact between each other, the two-photon energy, the energy of the two-photon pair, is pretty simple. It's given by the sum of the two individual energies. And the states we are interested in are states in which the two photons are emitted and propagate with the same momentum, or states in which photons are emitted and propagate with different momenta. And here I show you, and this is very important, the structure of the two-photon band. Simply, this is the two-photon band as a function of k and k prime running over the first Brillouin zone. And this structure is very important because some of its geometrical properties are linked to the emission dynamics that I'm going to explain to you. Very quickly, we observe that this structure is isotropic here, near its maximum, or near the minimum of this structure, but it becomes increasingly anisotropic if we move from the maximum towards the center of the two-photon band, where we can observe 4 saddle points. Okay, these saddle points, if you take the derivative of with respect to k and k prime in correspondence of a saddle points, we know that the saddle points is defined via the statement that the gradient is equal to 0 in that point, right? But this means, for example, that if we take the derivative with respect to k of these relations, we obtain that the photon is emitted with a 0 group velocity. And we will see that this fact will lead us to a non-Markovian dynamics. Indeed, this is the corresponding two-photon density of states. And we see that density of states exhibits various discontinuities. In particular, we observe jumps at the edges of the band, and these jumps are related to the already known fractional decay. But what is new in this system is that we observe a divergence at the center of the band, and this will lead to a new non-Markovian regime. And I would like to stress that in one-dimensional systems, the density of states does not manifest a divergence at the center of the band, always at the edges. Divergences of this kind are typical of higher dimensional systems, right? For example, two-dimensional system or three-dimensional systems, but never in one-dimensional ones. And for what concerns indeed the excited state populations as a function of time, we see that if the atomic frequency is tuned within the band, and we are sufficiently far from the center of the band, we observe a Markovian regime. This plot is in semi-logarithmic scale, so we observe an exponential decay of the atomic population. But if we tune the atomic frequency at the center of the band, here the red line, we observe that this decay is not exponential. And indeed, we enter a non-Markovian regime in which the excited state population decays very fast in a non-exponential way, but then we observe a small revival of the atomic population. To understand why we observe this non-Markovian behavior, we need to analyze the counterpart of the atomic population. Indeed, we ask what about the photons, how are they emitted and propagated in the array. Here, what I show to you is the field in real space. There is nothing but the probability distribution of observing one photon in a cavity and one photon in another cavity that are labeled by n and m here. The field in momentum space, that is nothing but the probability distribution in one photon with momentum k and the other photon with momentum k prime. And we start analyzing this pattern in the momentum space, and observe this pattern. Well, the answer is pretty simple. For the single photon, we know that when we set the atomic frequency at a certain value, there are two resonant modes with this atomic frequency, right? Now that we are working with a quadratic interaction and we are emitting two photons at a time, we need to identify our resonant modes. But now, if we take, for example, an intersection of an horizontal plane that is placed at the atomic frequency with our two-photon band, we observe that we have a continuum of resonant modes with our atomic frequency. And this pattern mirrors this intersection. It is nothing but the projection of this intersection onto the k and k prime plane. And most important, we are at delta equals 3j. That basically, this means that we are far from the center of the band. And what we see is that
this pattern is expected your emission.
Sorry?
This pattern affects your emissions.
Exactly. Not yet, but we will see that while moving towards the center of the band, these patterns will become very anisotropic by itself. And indeed, as Angelo said, this pattern here mirrors the isotropy of the two-photon band near its maximum. Okay, and the corresponding probability distribution in real space is isotropic. If we move towards the center of the band, the two-photon band will become less isotropic, And we will observe the same behavior for what concerns these two probability distributions. Since we are in the worst scenario that happens at the center of the band, in which the two-photon band is completely anisotropic, and we observe this very interesting pattern in real space that can be understood by this reasoning. We observe that the probability distribution of observing the two photons in the couple cavity arrays is non-negligible only along this diagonal and this other diagonal. This means that the two photons propagates or together along the same direction, or propagates with the same group velocity but in opposite directions. And this is closely related to the fact that if we are at the center of the band, for simplicity, we take omega c, the cavity frequency equals to 0. So the two-photon band is centered around 0. The condition such that the sum of the two energies of the two photons is equal to 0 simply implies that the energy of one would be equal to the opposite of the energy of the other photon. And taking the absolute value of the energies, they are related to the same modulus of the group velocities with which they are emitted in the array. And here we have quickly a summary of what I said. We start far from the center of the band. We observe anisotropic distributions, both in real space and in momentum space, and these patterns become anisotropically while we move towards the center of the two-photon band. But overall, the dynamics is simple to analyze if we study the photon density over time. For comparison, here I show you the typical photon density in an homogeneous couple cavity array with linear interaction. We observe that in that case, what I explained to you before is that we have one photon that is emitted from the atom, and the photon propagates along the array, either leftward or rightward. But in our case, we have two photons, and we have a continuum of resonant modes, and we have a continuum of different possibilities and combinations of group velocities with which these two photons can be emitted and propagate in the array. So, for example, we have at the center this bright line that corresponds to those couples that are emitted, and whose group velocities are very small, so they tend to stay around the emitter location, but eventually, over time, you see this bright region fades over time, so eventually even the lowest excitations spread along the chain. On the other part, on the other side, we observe bright region also here and here that corresponds to photons that are emitted with a greater group velocity and propagate faster along the array. This happens if we are far from the center of the band. If we are at the center of the band, the photon density exhibits an interesting behavior. We observe excitations that stay still around the emitter location. And after a finite time, we observe that the atom reabsorbed part of the excitations, and then this part of excitations is re-emitted into the array. Indeed, the excited state population as a function of time exhibits this non-Markovian behavior. It decays very fast, but non-exponentially. And after a finite time, we observe a very small revival of the atomic populations. And the reason why we observe this non-Markovian behavior is, again, related to that divergences of the density of states. The divergences of the density of states was related to the fact that at the center of the band, we have, among all the resonant configurations, 4 of them that are circled in red here. And these 4 configurations are related to scenarios in which the 2 photons are emitted still in the cavity of the emitter. They don't propagate in the array. So what is happening is that among all possible configurations, part of the excitations that are emitted into array remains still around the atom, giving the atom the time to reabsorb them and then re-emitting them. Very interesting, this behavior that I observed in an homogeneous coupled cavity arrays with 2-photon coupling was observed a few years ago, but in a very different system. In this article, the authors were studying the emission dynamics of an emitter linearly coupled to a square lattice, to a 2-dimensional coupled cavity array. And basically, as you can see, the results are exactly like mine results. So this means that the emission dynamics that I studied in a 1-dimensional coupled cavity array with a quadratic like matter interaction is identical to the emission dynamics of an emitter linearly coupled with a 2-dimensional square lattice. The only substantial difference is the decay rate. The decay rate in my system is twice the decay rate that they observed. And this factor of 2 is very important because it is linked to the statistics of the particles. It is linked to the fact that I have 2 photons in my systems. But nevertheless, the functional dependencies of the excited state population over time, as well as the probability distribution of the emitted field in real space and in momentum space, are exactly the same. Now I explain to you what happens if we take into account also photon-photon interactions in the cavity. And very quickly, again, now we are interested in the formation of 2-photon bound states, because as I explained to you, yes.
The computational reliability of the quantum two times
not the 2 in particular. It is more related to the fact that we have to take into account the statistics of having 2 photons. Okay. Very quickly, we are interested in the formation of 2-photon bound states. Why this? Because in the article of Peter that I was citing before, Peter et al. Studied the formation of 2-photon bound states as a second-order process, in which in the coupled cavity array they needed at least 2 emitters linearly coupled with the field. Now, with a quadratic interaction where an atom can emits directly 2 photons, the question is quite natural. Can an atom quadratically coupled to the field directly, as a first-order process, emit a 2-photon bound state? And the answer is yes. We observe the formation of the 2-photon bound states as a first-order process. And the dynamics that I studied is this one. We have the 2-photon continuum that would be here if, in any case, if we take into account carrier interactions or not. And if we take into account also photon-photon interactions, we observe the emergence of this band that it is nothing but the 2-photon bound state band. If we if we tune the atomic frequency in such a way that the only resonant states are the ones corresponding to two-photon bound states, we can neglect the contribution of two-photon scattering states. And what we observe is that in any case, the excited state population exhibits an exponential decay over time. We don't observe a non-Markovian behavior inside the two-photon bound states band, but only a Markovian regime in which the excited state population decays exponentially. And this is the decay rate that I was able to compute analytically. And very interestingly, it scales like the inverse of the sign of K0, where K0 is the resonant center of mass momentum of the couple, because now we have two photons. And for what concerns the emitted field, again, this is the probability distribution in real space. This is the probability distribution in momentum space. And this is a plot of the two-photon bound state dispersion relation as a function of the center of mass momentum. This is interesting because it only depends on the center of mass momentum, not also on the relative momentum of the two photons, but only the center of mass. And what we observe is that in real space, there is a non-negligible probability only along this diagonal. And this is exactly in accordance with what I've said before. Now the atom is emitting a two-photon bound state. That means two photons that propagate together along the chain. So we observe a non-negligible probability of finding the two photons only along this diagonal because they tend to stay in the same cavity and propagate together. In the momentum space, we observe these four bright lines, and to understand what on the resonant states, if we tune the atomic frequency, for example, here at the center of this band, we observe that in general, if we are not at the edges, we have four resonant states. Okay, these states are identified by a well-known center of mass momentum that I call K0. But if we look, una ciabatta? Presa? Ok, eccola qua. Ok. Okay, now that my computer is in charge, we're not in trouble. Oh, as I was saying, if we tune the atomic frequency, for example, here, there are four resonant states that are identified by a center of mass momentum that here I label it as K0. But if we now look at the probability distribution of observing one photon with momentum K and one photon with momentum K prime, we need to remember that K0 is given by the sum of K plus K prime. And this is nothing but the equation of a straight line in the plane. Oh. Okay. Okay. So, if without Kerr interaction, the emission dynamics of an atom quadratically coupled to the field was similar to the single photon emission dynamics of an atom in a two-dimensional lattice, okay? Now, with Kerr interaction, my emission dynamics with an atom quadratically coupled to the field resembles the single photon emission dynamics in a one-dimensional lattice. And indeed, one can show that if we consider the regime in which J is much smaller than U. That this means that we are interested only in the bound states without the contribution of the scattering states. The decay rate can be put in this form, where we can define an effective opting rate given by this ratio, J squared over U. But a one-dimensional homogeneous coupled cavity arrays whose single photon dispersion is given by this equation reproduce exactly the emission dynamics that I observe with an atom quadratically coupled to the field. And now, some of the ongoings that I'm currently focused on my PhD. The first question is, what happens if now we don't have one emitter, but we consider two or more emitters in my coupled cavity array? Well, without Kerr interaction, what I observed was that my dynamics was similar to an emission in a two-dimensional system, right? Now, with two or more emitters inside the coupled cavity arrays, this is the master equation one can write for the emitters subsystem. And despite the fact that this coefficient here is rather complex or not, the important thing is that this master equation describes this system. There is a set of emitters quadratically coupled to the field in a one-dimensional chain, but it also describes this system. There is a set of emitters linearly coupled in a two-dimensional square lattice, but except the fact that we have to pay attention on how the emitters are located in the square lattice. But nevertheless, this analogy is still valid. There is an emission dynamics in a one-dimensional system with quadratic interaction is similar, identical to an emission dynamics in a two-dimensional system with standard coupling. There is a linear coupling. If we now consider two or more emitters, but with photon-photon interactions, this is the master equation that one can write for the emitter subsystem, where we can identify a part with a non-emission Hamiltonian and this term that is known as recycling term. And the analogy here is still valid, is also still valid. That means that this master equation describes a set of atoms quadratically coupled to the field in a one-dimensional chain, and this dynamics is the same, is totally equivalent in a one-dimensional chain. So all the analogies that I observed during my thesis project are still valid if we generalize these analogies for two or more emitters. The second thing that I was currently focused on is this key idea here. That is nothing but the concept, the most important thing that I observed during my thesis project, that without Kerr interaction, the two-photon emission dynamics of an emitter coupled to a one-dimensional coupled cavity array resembles the single photon emission dynamics of an emitter coupled to a two-dimensional coupled cavity arrays. Now, this is my key idea, and I would like to generalize this statement to others one-dimensional coupled cavity arrays, because what I studied was an homogeneous simple one, right, with a single photon dispersion relation that exhibits only one band. But for example, if I consider a one-dimensional lattice that exhibits two bands with an energy gap, it is possible to construct a two-dimensional lattice that reproduces my dynamics with quadratic like matter interaction. And my idea is that this is possible, and now I will try to convince you also that this is possible. First thing first, the key idea is that the mapping of the dynamics is done by considering conceptually the two photons momenta, k and k prime, as the two components of a single photon that is emitted in a two-dimensional system. So k becomes kx and k prime becomes the component of the momentum along the y direction. And the other thing that is important is that the dispersion relation of the two-dimensional system, the single photon dispersion relation of the two-dimensional system, must be equal to the two-photon band observed in the one-dimensional one. The only problem is that a priori we don't know how to find or construct the right two-dimensional system that reproduces my dynamics. And I started from the SSH model. There is nothing but a very well-known model that exhibits topological properties, despite the fact that now we are not really interested in the topological properties. We are interested in see if that the two-photon emission dynamics inside these systems would reproduce a two-dimensional emission dynamics. And the SSH model, in terms of coupled cavity arrays, is nothing but a set of cavities that are arranged along a chain. But now the opting rates are different and they are alternated. We start from J1, then we have J2, J1, J2. And for what we are interested in, we consider only the bulk properties. So for now, we take periodic boundary conditions. We don't consider the edges of the chain, but we are only interested in the bulk properties and see how one atom put in the middle of the chain emits two photons. This is the single photon dispersion relation for the SSH model. And now it is more complex than having a single band. Now we have two bands, okay? And they are separated by an energy gap. This energy gap closes as the two opting rates are closer to each other. And here I plot the corresponding density of states as a function of the energy. And we see that, again, we observe divergences of the density of states only in correspondence of the edges of these two bands, okay? But this is a one-dimensional system, and this is what we expect, divergences of density of states at the edges of the band. Now, if I consider the two-photon subspace, so I'm interested in what are the energies, okay? Again, the energy of the pair is given by the sum of the individual energies, and now it is not trivial it is not trivial, the result, because we have two bands. So, for example, if one photon is emitted here, the other photon can be emitted here or inside this other band. So we need to take into account all the possible combinations of one photon emitted in one band and one photon emitted in the other band. If I call this E plus and this band E minus, this is the two-photon spectrum. We observe that we have one band identified by the sum of E plus and E plus. That is, the two photons are emitted in the upper band. We have this band here that means that the two photons are emitted in both in the lower band. And then we have all the combinations we can construct if one photon is emitted in the upper one and the other photon is emitted in the lower one. But nevertheless, this two-photon spectrum is far more complex than the one of the one-dimensional homogeneous coupled cavity array. Now we have three bands, and this is the corresponding density of states. We observe again jumps here, here, and here that are related to the edges of these bands that occurs at the edges of the bands. But more importantly, we observe divergences at the center of each band. Indeed, typical of higher dimensional systems. So what we expect is that, again, we will observe in a one-dimensional system with two-photon coupling a non-Markovian dynamics if we tune the atomic frequency here at the center of one of these bands. And indeed, this is the case. If we now put, for example, the atomic frequency here, and you see that at each color you see in this plot where the atomic frequency is tuned. If we are far from the center of the band, we again observe a Markovian regime. So the atom decays, the atomic population decays exponentially. If we are at the center of the band, but this occurs also if we are here at the center of the band or at the center of the band of this band, we observe a non-Markovian behavior that it is really similar. I observed during my thesis. The question is, are we able to construct a two-dimensional lattice that reproduces these dynamics if the atom is linearly coupled with the field in that two-dimensional lattice? And the answer is yes. We can construct the checkerboard two-dimensional checkerboard lattice that is constructed starting from this unit cell. This is a two-dimensional lattice that exhibits 4 sites per unit cells, and the single this equation. You see that indeed this is the same type of equation that identifies the two-photon energy, the two-photon energies for the SSH model, but now K and K prime are here Kx and Ky. So again, of the two photons as the two components of one photon that is propagating in a two-dimensional system. And what is really interesting about this system is that there is this article here in which the authors shows that also exhibits non-trivial topological phases. So this is interesting because one of the open questions of my PhD is that it is possible to exploit the quadratic coupling to investigate the so-called high-order topology. So topological properties that are typical of higher dimensional systems, relying on the fact that the emission dynamics in those systems are the two-photon emission dynamics in my one-dimensional systems. And this is a brief summary of the principal result of my thesis and my PhD so far. Without Kerr interaction, we have analogies with emission in two-dimensional structured photonic lattices. With Kerr interaction, we have analogies with single photon emission, again, in one-dimensional systems. And it also would be interesting, just for fun, to study what happens if we have an emitter that is quadratic coupled to a two-dimensional environment. Because, you know, if we are in 1D and we reproduce a two-dimensional dynamics, what can we expect from a two-dimensional system with quadratic coupling? As my super a four-dimensional emission dynamics, just for fun. And that's all. Yes, of course.
First idea of the something that I was thinking and didn't just yeah, so here since there is this kind of mapping between 1D and 2D, it might be interesting to look at the collective emission dynamics like the paper. The effect of collective variance is highly influenced by the
Okay.
so since there is
What I expected is that the behavior we observe in two-dimensional system, it will be observed now in one-dimensional systems with quadratic coupling.
And then one comment on the other project, maybe you know this already. I already some papers mapping between 1D model
Okay. Okay.
So there might be a partial answer.
Okay, okay. No, I didn't know, but I would focus more onto the other question, if it's possible to exploit topological properties of higher dimensional lattices. I'm not really interested in this mapping, but I'm more interested in the fact that we can exploit the properties of higher dimensional system with this type of coupling.
Yeah, no, the models are
Okay, 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 okay. Okay.
Can you tell more about how do you think to exploit product interaction gather information on your work?
Yes, I would like to, for example, we know that in the SSH model, if we consider an open chain, we can identify two different phases, and most importantly, the topological phase in which the system manifests the two edge modes, two zero energy edge states. In this article, they study the edge states that occurs in the topological phase of this two-dimensional lattice. And my answer is if with the two-photon coupling, I will be able to link these two types of edge states, the edge states that appears in the SSH model with the edge states that appears in this lattice. My answer is that if there is a link, a conceptual link between the formation of this kind of edge states. Exactly. If you consider this lattice, but it is open, you observe exactly corner states. Mamma mia che ansia, sto sudando, mi crede. Guarda qua, tocca qua.
C'è bisogno di
salutare pure amico.
Federico?
No.